Today we're going to talk about the fundamental theorem of calculus, which basically tells us how we can compute these integrals, these definite integrals that give us areas, without having to draw rectangles. So the fundamental theorem of calculus basically says you can compute the antiderivative and then plug in your bounds of integration. And so I'm just going to show you how this works by doing an example. So let's just look at example 1a. So to compute a definite integral, the first thing I'm going to do is find the antiderivative. So to integrate 5, I get 5x. If I integrate x squared, I get x to the third over 3. Now, with definite integrals, I'm not going to write down that plus c, because my definition actually says I can use any antiderivative. And so we might as well choose the simplest one, which has a constant of 0. And then the notation that we're going to use is I'm going to draw a little bar, and I'm going to put the bounds of integration, a 1 and a 3, on the top and the bottom. And what that notation is telling me is to compute this value, this area, I have to first plug in the 3. So 5 times 3 minus 3 to the third over 3. And then I plug in the 1 and I subtract those values. Okay, so finding a definite integral is now very similar to finding our indefinite integrals. We just have this extra step of plugging in these numbers, these bounds of integration. All right, 5 times 3 minus 3 to the third over 3 is 6. 5 minus a third is 4 2/3. 6 minus 4 2/3 would be 1 1/3. Or you could write that as 1.3 repeating. Example B, to find the following definite integral, the first thing I do is integrate. I have an e to the kx, e to the 5x, so I'm going to get a 1/5 e to the 5x. And then I'm going to have to plug in my bounds of integration, which are 4 and -1. So this is going to be 1/5 e to the 20th minus 1/5 e to the -5. This is now something that I would put into a calculator, and I got a pretty large number, 97,033,039. I rounded to the nearest whole number here. All right, example C. Now remember, there's no product rule or chain rule for antiderivatives. So if I want to integrate this, and I have a product, and I can't actually do the multiplication, I have to try that technique of substitution that we learned earlier. So I'm going to let u equal the thing inside the radical, 5 minus x to the third. My du is then negative 3x squared dx. If I solve for dx, I get dx is du divided by negative 3x squared. I'm going to rewrite my integral. It's x squared cube root of u, and then instead of the dx, I put in the du over negative 3x squared. I can tell substitution is going to work because the x squareds cancel out, and I have an integral that has u's in it only. So I'm going to pull the constant out front. I have a constant of negative 1/3, and I'm left with the cube root of u, which is the same thing as u to the 1/3, du. So to integrate, I'm going to get negative 1/3 times u to the 4/3 divided by 4/3. I don't really need the plus c. I have the habit of writing down the plus c, though, when I'm not plugging in numbers. I'm going to eventually plug in numbers, but I've left off those bounds of integration for a reason right now. Let's see, dividing by a fraction is the same thing as multiplying by its reciprocal. So I end up with a negative 1/4, and then I'm going to change the u back into a 5 minus x to the third to the 4/3. And now finally, once I have this thing back in terms of x, that's when I like to write down my bounds of integration. So the thing I wanted to point out with this problem is that the 3 and the 6, the bounds of integration, are x values. You have to write the problem in terms of x before you can plug those numbers in. And that's why I had the habit of not writing down those numbers when I had u's, because I didn't want to accidentally plug them in for the u. All right, so I have to plug in the 6, and then I have to plug in the 3 and subtract these antiderivatives. I definitely need a calculator for this one. And I ended up getting negative 298.63. That's rounded to the nearest hundredth. Now, why am I getting a negative answer if definite integrals give me area? The reason I'm getting a negative answer is because this means the function is below the x-axis. So when you add up those y values, they're actually negative numbers. So it's okay to get a negative answer. It just means your function is not above the x-axis, it's below it. And so I have listed a couple other properties of definite integrals. The first property says, let's say, for example, you are integrating from 1 to 4. You could do this as two separate intervals. You could integrate from 1 to 2, and then integrate from 2 to 4, and add those things together. So you can always integrate in separate pieces. The second property says if you switch the order of the bounds of integration, you get an answer with the opposite sign. And then the third and the fourth properties is what I was trying to mention earlier. If your function is positive, the answer you get is the area. If your function is negative, you get the negative area. So let me try to explain that with an example. Let's use the following graph to find the integrals. So if we integrate from 0 to 2, notice the function is above the x-axis, and so our answer is just going to be that area, which they told us was 2. If we integrate from 2 to 4, the function is now below the x-axis, and so our answer should be the negative area, or negative 5. If we integrate from 4 to 5, the function is again above the x-axis, so our answer is our area, which is 2. Now, if we want to integrate from 0 to 4, we can add those two separate integrals. So from 0 to 4, we would get the positive 2 plus the negative 5, or negative 3. The negative answer tells me from 0 to 4, more of the function, more of the area, is below the x-axis. And finally, if I want to integrate from 0 to 5, I could add up my integral from 0 to 2, plus my integral from 2 to 4, plus my integral from 4 to 5, and I would get an answer of negative 1. All right, so let's do an example of an area problem. We're going to find the area between the x-axis and the following function. And so I'm going to start to draw a picture, really because I want to know, is this function below or above the x-axis? And so to help me, I'm actually going to set this thing equal to 0. I'm going to figure out where the x-intercepts are. And I can factor out an x. So that tells me I have x-intercepts at 0 and 8. This is a parabola that opens up. So that means part of the graph has to be below the x-axis, part of the graph is above. In this problem, we want to find the area between the x-axis and this function. In this problem, I want to find the area between the x-axis and this function. Part of that area is above the x-axis, part of that area is below the x-axis. And so if I want to get the total area, I'm actually going to have to do two separate integrals here. If I just integrate from 0 to 10, I'll have a negative area plus a positive area, and those things are going to cancel out. So you have to do the negative region, which is from 0 to 8, and the positive region separately. So I'm going to start by integrating the function from 0 to 8. If I do this correctly, I should get a negative answer. So let's see, if I integrate, I get x cubed over 3 minus 8x squared over 2, or x cubed over 3 minus 4x squared. And I'm going to have to evaluate at 8, evaluate at 0, and subtract them. So let's see, that's 8 to the third over 3 minus 4 times 8 squared minus, if I plug in 0, I actually just get 0 here. So that is negative 85.33. I'm glad I got a negative answer because the function is below the x-axis. Okay, now I'm going to integrate the region that's above the x-axis. So I'm going to integrate from 8 to 10, the exact same function. So I still get the same antiderivative, x cubed over 3 minus 4x squared. But this time I have to plug in the 10 and the 8. And so if I plug those numbers in and put this into my calculator, I ended up getting 18.67. Finally, to finish this problem, I'm going to take the absolute values, so I'm going to ignore the negative, add these numbers together, and that will give me my total area. So 85.33 plus 18.67 equals 104, and that is the total area between the x-axis and this function. Let's do another example. So I want to start by finding the x-intercepts. I always want to start by setting the function equal to 0 so that I'll know where it crosses the x-axis. Okay, so add the 1, then I'm going to take natural log of both sides. Natural log of e to the 2x is just 2x. Natural log of 1 is 0, so it looks like x has to equal 0. So this function crosses at the x-axis. It's an exponential function, so it's increasing. And so the graph looks something like this. I want to find the area between this function and the x-axis from negative 2 to 4. And so I'm going to have to do this as two separate integrals as well. So I'm going to start with the region that's below the x-axis. So that's negative 2 to 0. And I'll integrate my function. And then I'm going to have to integrate the region that's above the x-axis separately. So to integrate e to the 2x, I get a 1/2 e to the 2x. If I integrate 1, I just get x. And I'm going to be evaluating this at 0 and at negative 2. If I plug in 0, I get 1/2 e to the 0 minus 0. I plug in the negative 2. I put this into my calculator, and I got approximately negative 1.5. Then I'm going to integrate the region that's above the x-axis, so that would be from 0 to 4. I should get the same antiderivative, 1/2 e to the 2x minus x. The thing that's different is my bounds of integration. I'll be plugging in 4 and 0. I use a calculator to help me with this part, and I get 1486. Finally, to finish the problem, I have to add the absolute value of those answers. So the area is going to be 1.5 plus 1486, which would be 1487.5. And that's my final answer.